Hello and welcome. Today we're going to be looking at the unit test for types of interactions. This is one of the topics in physics. It's included in both general and honors physics. As always, we're going to be going through all of the questions on this unit test to make sure that you understand how to approach and solve these questions and are ready to ace your physics exam. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our first question. Here we go. Two masses, one of mass m and the other of mass 4m, are positioned as shown in the figure. 4 points A, B, C, and D are located along the straight line that passes through the center of each mass. Point C is an equal distance from the center of each mass. Points A, B, and D are all the same distance from the center of mass closest to them. Alright, at which point will the gravitational field be the strongest? Alright, so how are we going to approach this kind of problem, So we can figure out how much, relatively, how much the gravitational field is for each one of these points. All right, so at point A, you have 4m, mass of 4m. All right, and we the rest of the gravitational equation for a gravitational field is we have g times big M over r squared. Now this big M here is going to be this mass right here. So we can call g over r squared just x. We're going to call this x. Sorry, we are going to call this x. So the attraction between this and this is going to be 4x. 4x. Okay? Now for this one right here, it's going to be 1, 2, 3, 4, 5 away. Alright, so now by the inverse square rule, the rule that says that as we get farther apart, we have to divide the force by the square of that, right? So we're going 5 more up away from where we were at, so we have to divide by 5 squared, or 25. That's this over r squared right here. That's where that comes from. So it's going to be something over 25. Now, since this is just m mass m, not 4m, it's just going to be x. Remember, x is that g over r squared. And you're going to add these two because they're both an attractive force. So they're both going in that direction right there. Okay, now for B, you have 1 away from here, so it's still going to be the 4x. And then here you got 1, 2, 3 away, so it's going to be x over 9. But this one is taking B in this direction, and this mass is taking B in this direction. So you have to subtract 4x minus x over 9. And then for C, well, it's 2 away from here, so divided by 4. 2 away from the other mass, so you have to divide that one by 4 as well. So you get 4x over 4x minus x over 4. All right. Now for D, you are 1, 2, 3, 4, 5 away. 5 away from this 4m right here. So that's going to be 4x over 25. And then you're going to add back. It's 1 away, so it's just going to be plus. It's going to be plus an x. So you're going to add back x. Okay? So that gives us A is going to be 4x plus x over 25, B is 4x minus x over 9, C is x minus x over 4, and D is 4x over 25 plus x. Right? A and D have a plus because they're both going in the same direction. B and C, they're going in opposite directions, so you have to subtract them. Now the one with the biggest force is going to be 4x plus x over 25, or point A. So that's going to have the greatest gravitational field, strong gravitational field, and we can keep going to the next question. Right, a 1,500 kilogram satellite is in orbit around Mars at a distance of 2 Mars radii above the surface. Mars's mass is 6.42 times 10 to the 23rd kilograms, and its radius is 3.39 times 10 to the 6th meters. Calculate the magnitude of the gravitational force acting on the satellite. Alright, so what we're going to do here is we're going to write down the gravitational equation. Right, how are we going to do that? Well, the formula for the magnitude of the gravitational force is the gravitational constant g times big M times little m over r squared. Okay? So that's going to be the gravitational force G is the gravitational constant is 6.67 times 10 to the negative 11. If you're on a physics exam and you need this number, you don't really have to memorize it because you'll probably have a reference sheet saying what this is. Right, then you have to multiply by the big mass of Mars, 6.42 times 10 to the 23rd, and then by the smaller mass of the satellite, 1,500 kilograms, over r squared. Well, the radius here is going to be 3.39 times 10 to the 6th times 2 Mars radii. All right, so 3.36 times, or 3.39 times 10 to the 6th meters. That's going to be the radius at this point. Now we're a distance of 2 Mars radii above the surface. So if we drew as a circle, you're up here. So you have 1, 2, and then a third Mars radii distance. That's the distance. You have to multiply by 3, and then you're going to square that. Then you square that to get the total gravitational force. So it looks something like this right here. That's what it looks like. Okay, so if we take that and we just compute that, right, we can pull out a calculator and see what that is, okay? So we have 6.42 times 10 to the 23rd. 6.42 times 10 to the 23rd times 1500 over 3.39 times 10 to the 6th times 3 squared. And then, of course, you're going to multiply by the gravitational constant, 6.67 times 10 to the negative 11, which gives you 621 newtons as the gravitational force. And we can keep going to the next question. Two identically charged balls are separated by some distance r between their centers and exert some force F on each other. The balls are then pulled apart to create a new distance between their centers of 1.5 r. What will the new force that the two balls exert on each other be? Remember that we have the inverse square rule. As you increase the distance, you're going to decrease the force by dividing it by whatever you have, by dividing it by whatever the distance is squared. So we have times 1.5 squared, so that's going to be 2.25. So you're going to divide the force by 2.25. So if we do the F over 2.25, that's going to be that answer. So we can keep going to the next question. All right. Now, our question is, a very strong bar magnet is moved quickly in and out of the center of a coil of copper wire. Which two pieces of evidence would indicate a current was induced in the copper wire? All right, let's see. So if an ammeter in the circuit with a coil of wire shows a current, well, that would definitely show that there's some kind of current in the copper wire. And if the light bulb in the circuit with the coil of wire lights up, that would also indicate that. Alright, so that's how we know that a current was induced in the copper wire. Two coins made of different materials are placed next to each other so that they are touching. Both coins are 15 millimeters in diameter. One coin has a mass of 6.5 grams, and the gravitational force between the coins is 4.03 times 10 to the negative 11 newtons. Calculate the mass of the second coin. Let's see. So, you have the coins are touching. Alright, so each coin is 15 millimeters in diameter, or 7.5 millimeters radius. So the distance to their centers is going to be the 15 millimeters again, or 0.015 meters. Now the coin has a mass of 6.5 grams, or divided by 1,000, 0.0065 newtons. That many newtons is what you have. Now, if you have, not newtons, that's how many kilograms you have. Now the gravitational force between the coins is 4.03 times 10 to the negative 11. We're going to have the mass of the first coin times the mass of the second coin, which we don't know, over 0.015 squared times the gravitational constant equals that 4.03 times 10 to the negative 11. All right, let's divide by the gravitational constant, get that out of the way. Get that out of the way. And we find that now we have 0.604. That's going to be the two masses multiplied over the radius squared. We can multiply both sides by the radius squared, and now we just have to find the product of the two masses, the two coins. So we divide by the mass of the first coin, and that gives us the mass of the second coin to be in grams, multiplied by 1,000 to give it in grams to be 21 grams. And we can keep going to the next question. Points A, B, C, and D represent different locations near a permanent magnet. Which of the following statements correctly compares points C and D? All right, let's see. So C is getting this force. It's closer to the magnet than D is, so it's going to have more of a force. So it experiences more force than D. Right, so it's not going to be B because that says less force. C and D say approximately the same amount. So that's also going to be incorrect. So the answer is more force, which is choice A. Let's keep going. Two charged soap bubbles, bubble 1 and bubble 2, separated by a distance r. Bubble 2 has 8 times the charge of bubble 1. Bubble 1 exerts a force on F1 to 2 on bubble 2, and bubble 2 exerts a force F2 to 1 on bubble 1. How does the magnitude of F1 to 2 compare to F2 to 1? Well, these are just going to be opposite forces, right? They're forces that act on the same things oppositely. They're the same type of force, and one of them is one on the force of 1 on 2 and the force of 2 on 1. These are opposite forces which are going to be the same by Newton's third law. So they're going to have the same magnitude. Let's keep going. Imagine two pairs of books. In the first pair, two books of mass m1 and m2 are separated by the distance r, resulting in the gravitational force F1. In the second pair, two books of mass 2m1 and 4m2 are separated by the distance 2r, resulting in a gravitational force of F2. The relationship between these two forces can be written as F2 equals nF1. In the expression F2 equals nF1, what is the value of n? Let's see. So the first pair has has masses of 1, 1, and then the distance is 1. Second pair, you're multiplying the mass by 8 in total, and you're dividing by the distance by 2. Well, the mass is just going to be multiplied, that's the singular thing, right? So times 8. The distance is going to be squared when you divide it, so 2 squared is 4, so you're going to be dividing by 4. 8 divided by 4 is 2, so our answer here is going to be 2. And we can keep going. A nickel carries a charge of negative 1 times 10 to the negative 9 coulombs. A dime carries a charge of 1 times 10 to the negative 11 coulombs. The two coins are placed near each other, and the magnitude of the electric force between the charges on them is 2 times 10 to the negative 6. Calculate the distance between the two charged objects. Alright, so we know that we have 1 times 10 to the negative 9 times 1 times 10 to the negative 11. We can get rid of the negative sign because we're taking the absolute value of it anyway. And then we get 1 times 10 to the negative 20 times the electrical constant, 9 times 10 to the 9, and that gives us 9 times 10 to the negative 11. And that's going to be divided by the distance squared, which is going to equal the force. So we divide by the distance squared equals the force. So 9 times 10 to the negative 11 over something squared equals 2 times 10 to the negative 6 squared. So if we divide both sides by 2 times 10 to the negative 6 and multiply both sides by r squared, then we get that r squared is just going to be equal to 4.5 times 10 to the negative 5, and r is going to be 7 times 10 to the negative 3, and we are done. Alright, so that was this unit test on types of interactions, mainly focusing on magnetic, electrical, and gravitational. So that was this whole unit test. I hope you learned something from this video, and I hope you enjoyed it. And I'll see you next time when we continue looking at more physics topics. I'll see you then.